Hello, everybody. I'm Michael Short. Welcome to the, I'm not sure what number webinar we're on, but this is the AI for Net Zero webinar series on YouTube. I have Professor Ahmed Al-Sheikh from Harayat Watt University with me, and we're chairing today. The webinar series is designed to bring together experts, innovators, and enthusiasts from both the artificial intelligence and sustainability domains, with an overarching goal to accelerate progress towards net zero targets. The series aims to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. The webinar series will delve into the diverse applications of artificial intelligence across various domains, crucial to achieving net zero targets, including energy, transport, environment, agricultural, and food systems. So I've got the pleasure of introducing Dr. Amin Zarei as our first speaker. We will also have a second talk after that from Dr. Max Weissenbacher. Dr. Amin Zarei is a research fellow in the Department of Chemical Engineering at the University of Surrey. Previously, he was postdoctoral fellow at Chong'an University, following his PhD from Pukyong National University, both of those in South Korea. He has extensive experience in renewable energy supply chains, focusing on hydrogen, biofuel production, and carbon capture. So the floor is yours, Amin. Welcome.
Thank you, Michael. It's my pleasure to be here and present my last research. Okay, if you don't mind, I start my own presentation, which is about the dynamic optimization of biogas production and CHP utilization in the digestion system. So today I want to talk about one of the most important issues in our decade, which is finding the renewable energy resources to feed our society. So basically, before starting my presentation, I would like to have some brief introduction from myself. I'm Amin, as I said. I'm Iranian, was born in 1990, got PhD back in Korea, and got my master in Iran. As you said, I am now research fellow at the University of Surrey under supervision of you. And before that, I was postdoctoral fellow in Chong'an University, and also have some industrial experience back in Iran. Starting my presentation, let's see what we have today. I'm gonna start with introduction, then going for my model presentation, then explain my case study, result, and conclusion. Introduction. So here you can see the energy flow chart of the UK. As you might say here, that's a huge amount of energy that we need for the country. That's 3,000 terawatt hours. And as you can see here, the bioenergy is a small part of this energy resources. Despite of all the fact that UK is pioneering in renewable energy, but here you can see how we are small, how we have difficulty, and how small is portion of the renewable energy, specifically bioenergy. However, in UK, as I said, there are a big step to reducing the carbon emitting energy resources. As you see here, in the UK, they just remove the coal from the resources, from the energy mix. And also you could see how the bioenergy increases during our previous decades. So you can see that there is a future for bioenergy, and that's it. This portion of the bioenergy could be increased. As I said, the UK is so dedicated to producing the carbon zero energy. As previous March, 47% of the power came from the net zero carbon. Also, new record was made by this March that 67% of the energy of national grid came from the wind. And also, you can see in that March the breakdown of the UK electricity supply chain generated. And as you can see here, the largest portion for the renewable energy dedicated to biogas, which means that in the UK there is a huge investment on producing the biogas. As the facts shows that anaerobic digestion, which producing biogas, has over 65 plants in the whole country, and it produces 50 to 100 gigawatt hour of energy in 2020. And it directly followed the carbon neutrality goal in the UK, because this AD technology is crucial to reducing the dependence on the fossil fuel and lowering greenhouse gas emission. However, there are some challenges in producing the biogas by AD plant, such as complexity, feedstock availability, model dependency, and energy maximization and supply chain issue. So, in my model, before starting to present my model, let's see what is real-time optimization. First of all, let's see how anaerobic digestion works. In anaerobic digestion plant, we can start from as you can see in the middle, we have the plant, middle that we have feedstock that come to the plant. During the process, it produces biogas. This biogas can inject it to grid to fulfill the demand. Also, this biogas can go through the CHP power plant to produce the power. And again, it can fulfill the demand. And the digested of the anaerobic this plant can go to the farming and those stuff, and again make food, and again going to meet the demand. And also the feedstock, the slurry of the those farming can go to make their recipe of the input in anaerobic digestion. But what we do, we are doing real-time optimization on this 8 plant. Generally, real-time optimization has 3 main issues, which is optimization, simulation, and predictive control. In this process, the real-time optimization, this process is continuously monitor and adjust operational parameter in a real time to enhance the performance and efficiency of the system. By utilizing data from sensors and applying advanced algorithm, this method can predict outcome and make instant adjustment to optimize the process, which is in our model is maximizing the biogas production, reducing the energy consumption, and also lowering operational cost. Let's have an example about this real-time optimization in the AD plant. Let's say in a real-time optimization, we can increase the biogas yield by 50%, which means that we can have additional 1,200 cubic meter biogas per month based on the 8,000 meter cubic production. That means that we have 15% revenue improvement, 12% reduction in energy consumption, and 10% decrease in operating costs. Eventually, we have 10% reduction in greenhouse gas emission. So you can see how this model can work to optimize the model to reducing costs and increasing the sustainability. So talking about this introduction, let's focus on our model production. My model, the model I developed here is the anaerobic digestion for co-digestion for co-substrate, which the objective function here is the maximizing profit, whereas minimizing cost and minimizing the global warming potential. In the model, the feedstock can go through the anaerobic digestion, also can store in the storage, and then after processing and making biogas can go through the CHP to make power and heat, also can go through the biogas after some purification, and also the digestion can go to meet the demand for fertilizer demand. Going through the model, I use the first order equation to make prediction for the co-digestion, and also in order to incorporate temperature and pH, I use the data-driven model approach called CTPM to engage the temperature and pH to the model. Also, by applying the the energy balance, I can monitor the temperature of the process to have the optimized temperature by heating or cooling. As I said, the objective function here is increasing the profit along with decreasing cost and also decreasing the global warming potential. This profit is including the profit of the CHP and profit of the gas. The cost is included as cost of substrate, temperature, pH adjustment, and CHP startup and operation maintenance, and the digester operation maintenance cost. And the global warming potential, including the cultivation, transportation, CHP leakage, and so on. After that, we implement our model to the case study, which assume that those temperature and energy price and availability of the model, and also the from the parameter that we got from the techno-economical assessment group that I added to this model. I just defined two different scenarios, which is dynamic and steady state. In the dynamic model, we just assume the model just going to start, like just establish the plan, or we are in overall haul, which we again need to open we need to start from the beginning, the digester, and we want to see how it works, how the model works in this situation. We are looking for track the level of digester in each time period, ensuring the mass balance with the every fluctuation in the inflow and outflow of digester. And in a steady state, we just assume that the anaerobic digestion process is under steady state condition, ensuring the consistency and simplicity in operation with the digester that is already full and operational. In the steady state model, we assume that the inflow and outflow are equal. It is in steady state condition with the minimal adjustment. And the starting point here is with fully operational digester simulating normal operational cost, normal operating condition. Result. Let's start from the statistics of the model. In this model, although we have nonlinearity in this model, but because we just remove the binary variable, you could see here the computational time is so low, which is good, which is good news. Also going for the objective function, which is the profit total cost, you could see here that the steady state model followed some trend that it is there's no fluctuation. However, in the dynamic model, we have the fluctuation almost in 40 time period, which is here, it means day 40, we have some fluctuation. And also this fluctuation affected total profit. You can see here in steady state, we have more profit. However, because here in our model, the CHP has more profitable, this fluctuation doesn't affect the CHP production, and it affects the profit of the biogas. You could see here that the dynamic model has the less production of the biogas. This fluctuation affected the feedstock using. In this case study, we used maize and manure as our feedstock. And you could see here that this fluctuation affected here. The reason of this fluctuation is that there is a definition in the anaerobic digestion called HRT, which stands for the hydraulic retention time, which introduced the rate, the flow rate of for how long the feedstock can remain in digester. Which here we define the boundary for this value. As long as the outflow started. So this outflow affect the HRT, which going to increase HRT. In order to decrease the HRT to not to touch the upper bound, we need to increase our inflow. In this model, as I defined, the feedstock, the manure has more density, the feedstock, I mean. However, the maize has more productivity. So you can see at the beginning, we have no problem for the HRT. We use whole our maize. But as long as we have problem with the HRT to not to touch the upper bound, the model preferred to use the manure to increase the inflow by using the manure. However, as I said, the manure doesn't have good productivity. Doesn't yield well. So increasing manure means less production, less producing biogas. In this case, you can see that there is the same level of the production biogas, but in dynamic model, we have a gap here. But as I said, because in this model, the CHP has a higher profitability to produce electricity and heat, it doesn't affect the CHP. In both steady state and dynamic, we have the same amount of the CHP production. However, the selling biogas from dynamic model and steady state, you can see here that in dynamic model we have less selling amount in the to the market. At the end, the result of the global warming potential shows that the cultivation, transportation, CHP and CHP production and leakage has main concern. In these four concerns, you can see here that the transport here has the most disaster here, I can say. Which we in the next step we need to focus on this supply chain to see how this transportation can help to reduce the GWP. Also, here CHP GWP for CHP, both of them are same, but in order to some clarifying, I just make separate them and make stacked line to show both of them. In conclusion, I just developed a nonlinear optimization model for anaerobic co-digestion by using a CTPM approach, data-driven approach that I implemented temperature and pH to the model. And also I compare steady state and dynamic model to see how it's different and how it works and how we can optimize this co-digestion. In the future, we need to focus on the sensitivity and on certain parameters, and also to check how the model act if we add more feedstock. At the end, I would like to have some brief discussion about the project that we are working on. We are working on that. In this project called AR for Net Zero, artificial intelligence enabling future optimal flexible biogas production for net zero. That's too much, I know. In this project, we will develop a new tool to increase flexibility and profitability for the anaerobic digestion. For the UK, we plan to link this various feedstock, as I said, to the microbial population and the productivity of the biodigester, along with developing whole system of the anaerobic digestion plan. Also, we plan to do this by developing decision-making tools, including uncertainty, hybrid machine learning, and also optimization-based model for feedstock procurement and operation of real-time optimization that I presented here. In this team, there are some group from University of Surrey that head of group is here. Dr. Short, as a PI of this project, is in University of Surrey. Also, there are some group in Southampton University, Manchester, and Nottingham. And also, we have some industrial group, such as Future Biogas and etc., to help us to make the realistic model. Thank you so much for joining, and I will be here to answer the question.
Thank you very much, Amin. Very nice, clear talk. I think, let me first see if we've got any comments in the question box. If anybody online that is watching live, you can post your questions in the comment box, and we can ask them to the speaker. In the meantime, maybe I'll ask the other people in the room if they have questions before I ask, because I know quite a lot about this project.
Yeah.
Yeah, sure.
So small comments for people who are on YouTube: you need to sign up using your email before posting your questions. So please post your questions if you can, if you have a question. So thank you, Amin, for the very interesting talk. My question will seem a little bit odd, because I'm aware of the work you have done. I've read I've seen this before, but my question for you as a researcher: have you interacted and learned about this topic from the industrial partner? What kind of interaction you have had, and how it's informed your own research?
So that's a good question. We have a tight connection with our partner, industrial partner. Also, recently there is an industrial partner, the industrial secondment, that she joined our group, and that was so practical, because when the academic are just made a model, we don't know really the practical term, and we don't know what's important really in order to in real operational. But in contact with them, they can focus on that one. This is important. This part is important. We had challenge in this part, and we need to cover this issue. So that I can say that that's really helpful for me to make my model.
Yeah, because we are in academia, we are after novelty to publish papers. And in industry, they are more about robustness and feasibility of the application. So it is really important. Yeah, we definitely need to progress our academic career by developing new methods, but when it's guided by real demand from the industry and application, this is where the biggest impact comes in. So it comes in uncertainties in the data. It comes in feasibility of the control signals you give or the results you give. Can you change things significantly in short period of time? For mathematics, yes, it's a number, but for application-wise, it is operational constraint.
True.
Yeah, and then maybe I can ask kind of a question for some of those that might be more on the interested in the methods. How do you find what are the biggest challenges with implementing a model like this? And what are the chances of finding, for example, local optima? You're solving very quickly, but how can you? What are the kind of methods that you're using to solve the problem?
That's a good question. So first of all, I use different technique, and because it is non-linearity, first of all, we need to reduce this headache like binary variable or this stuff to increase our solution, decrease computational time. And also I checked with some data sets to see how it goes, some kind of, let's say we can say a Bayesian optimization, to see how it goes, how it is reasonable or not. And based on what I got from my result, I can modify my parameters to see what was the result again. And gradually I modified it and get the best solution, hopefully. However, there are sometimes that we stuck in the local optimization, which which I can say that there is an issue, and I try to make some data set that far from the data set I find, that I can see that if I try the some different in different value, how it works. So this kind of thing that I can find, that I can get out of the local optimal solution.
Okay, so I guess it's like multi-starting, right? You start the algorithms because they're gradient-based methods. You
Exactly.
start at different initial points.
Exactly.
I think we've got time for possibly one more question. I don't know if anybody in the room has a question, because I can't see any questions coming from online.
Yeah, I have a question. Once you analyze multiple problems, can you somehow build an intuition into simple solution or simple rules you can advise practitioners? Is that something you have worked on or have seen people working on?
The thing is, what I found from my work is better to start from the toy problems that simplify the model than gradually make it the real-time optimization. In that case, you can see the errors, you can see how this model works well, because in toy problem, you can just solve it by your hand. So you can just check it out if it works or not. And step by step, when you make it bigger, and you can 100% sure that this model works well. This is what I found.
Yeah, thanks, Amin. Cool. So I think we can probably move on to the next talk. I'm very happy to introduce Dr. Max Weissenbacher. He's a research associate in the Department of Aeronautics at Imperial College, and works on control and reinforcement learning for chaotic systems as part of the AI for Net Zero project. His research combines deep learning with mathematical physics. Prior to joining the AI for Net Zero project, he completed his PhD in mathematics at Imperial College London on the stability of black holes. I'm very interested now in hearing your talk, so I'll hand it over straight to you, Max.
Thank you, Michael, and thank you to the organizers for having me, and also Amin for this very interesting talk. That was super interesting. Yeah, so I'd like to talk a little bit about the research that we've done in the group on applying reinforcement learning to turbulent flow control. And I'd just like to start off the talk basically by just giving two, I think, really cool applications that sort of highlight the potential impact that turbulent flow control can have on this net zero transition. And then I want to talk a little bit more about a specific, about the specific challenges that come with it and how we might go about addressing them. All right, so, Okay, so the first application I would like to highlight is road vehicles. So in road vehicles, the aerodynamic drag causes typically up to 70% of a vehicle's energy consumption. Now, this is obviously a very, very kind of ballpark type of number. It depends on the specific vehicle. It depends on the load, the velocity it's traveling at, and so on and so forth. So many, many different things. Now, of course, people have been thinking about this a lot, and one particular application is heavy goods vehicles, HGVs. And one particular way of dealing with this that's getting more and more popular is called static boat tails, or boat tails, which are basically just sort of a polymer plastic attachment that goes at the end of the trailer that sort of tapers inwards a little bit like this. And this can actually save up to roughly 10% in drag. So one question that we're trying to investigate, or that's been increasingly investigated as well, is what if we move from a static shape to a dynamic controller? So as you can see here, this little truck has basically all kinds of pressure sensors attached to it, as well as dynamically movable flaps. And the question is, if we find some kind of closed loop active control strategy, can we get more drag reduction? Just as an example of the impact this could have, consider typical fuel consumption of an HGV. Imagine that again, imagine you could achieve a 20% reduction in drag, so more than a boat tail. That would save you, again, very, very roughly speaking, around 10% of your fuel consumption, which would not only save tremendous amounts of money, but would also cut something like 70 grams of CO2 emissions per kilometer traveled, which, for a typical HGV might add up to thousands of kilograms or tons of several tons of CO2 and other greenhouse gases each year. Now, another really cool application is our wind farms. So in a wind farm, the total power output is typically only around 50% of the theoretical power capacity, where the theoretical power capacity is computed by simply multiplying the power capacity of a single turbine by the total number of turbines. The reason for this, you can see well in this picture of a wind farm that was taken in some specific weather conditions that allow you to see the flow somehow. And the reason is that essentially the frontmost turbine generates a lot of turbulence in its wake, which then essentially lowers the power output of the subsequent turbines, thereby lowering the total power output of the farm. So again, this is a very active and very interesting field of research. A way to address this is called static wake steering, or wake steering, where the idea is that if you look at this LES simulation here of a wind farm, the idea is if I rotate one turbine a little bit, that the wake shifts a bit, that lowers the output of the first turbine, but it increases the power output of the second turbine, thereby increasing the total output of the farm. And again, the idea is, can we move from a static setup to a completely dynamic setup where the turbines could find a more effective strategy by moving dynamically and or by potentially adjusting to different wind conditions, wind speeds, wind directions, and so on. As a little example computation, consider, for instance, the London wind farm array, which is on the UK coast, and consider the scenario that for some reason or other you could do something to make to increase the total farm output by 20%. That would actually amount to 40,000 additional homes that could be powered and heated each year in the UK. So again, I think really a lot of potential impact. Now, both of these projects I mentioned are, I posed this as a question for a reason, because this is like very much like ongoing projects that we're working on. I can't really tell you the answer, but what I can tell you is how we're trying to do it, which is with the use of reinforcement learning. So reinforcement learning is actually a very general purpose optimization technique that sits somewhere at the intersection of machine learning and optimal control. And the way that we model the optimization problem in reinforcement learning is we have something called an environment, or more formally a Markov decision process. So if you know what a Markov process is, a Markov decision process is basically the same thing, except that the state at time t+1 is not fully determined by the state at time t, but instead by the state at time t plus an action, or a controller input, which has to be decided by a certain controller. So diagrammatically, we can display it as in this little diagram. So we have this environment. At each time step, we have this loop where the environment informs the controller of the state it's in, ST, and it also gives it a reward, RT. The reward is essentially just telling you, am I in a desirable state or an undesirable state? The agent, or the controller, right, then needs to takes this as an input and needs to decide on an action to take, which is then executed in the environment and updates the environment state. The agent is then updated so that the cumulative reward, or the sum of the rewards, is maximized. So a very famous example, the video isn't working here, unfortunately, but a very famous example from around 10 years ago is when, for the first time, we could train a computer to actually play Atari games at human level or better. So this game is called Breakout, and some people may or may not have played this on their phones at some point. But basically, sort of the agent starts out taking actions which are completely random, and then through collecting experience and collecting this reward signal, sort of successively becomes better and better, and will start taking actions which will maximize the cumulative reward. Okay, let's talk about what are the challenges in realistic turbulent flow control. So well, yeah, as the title of the slide says, realistic turbulent flow is challenging for many reasons. The first two reasons I want to highlight is that turbulent flows are intractable, which means that simulating them on a computer is extremely computationally expensive. So unfortunately, at the same time, most or all reinforcement learning algorithms are very sample inefficient, which means that they actually need to collect a lot of experience. They need a lot of interactions with the environment in order to converge and in order to learn a policy, or in order for the agent to learn to behave in such a way that the reward is actually maximized. So this is obviously immediately a huge problem. Next, there is a problem that's just inherent to turbulent flows, which is that the effective dynamics is extremely high dimensional. So in a more technical wording, you could say that the inertial manifold of turbulent flows, or these control problems, is very high dimensional. So what this means effectively, if you think back to the Atari game, if you try to, there are several ways you could represent the game. One is the visual way, which we humans like, right? But if you wanted to, you could cook up a very, very low dimensional representation of the game state. Certainly, I don't need to look at all of the pixels of the entire game. I probably just need to know where is the little paddle that moves around, where's the ball, and where are the blocks. So this is a low dimensional presentation. Within turbulent flow, this is of course entirely impossible. Almost, by definition, the effective dynamics are extremely high dimensional. There's two more issues that I want to highlight using this wind farm LES simulation from before. So one is time delays. So turbulent flows, or fluid flows in general, have this transport component, which means that if I look at this wind farm, for instance, if I make a change here, so if I rotate my first wind turbine, it will actually take some amount of time for this change to somehow propagate along the wind farm, and it will take some amount of time for this change to actually reach the second turbine. So this means I somehow need to have some sense of what happened in the past and what's going to happen in the future. So this immediately creates more challenges. Another challenge is that of partial sensing. So in any realistic application, I will only be able to sense the state of my turbulent flow in a very few, very limited locations, right? So of course, if I have a simulator, I could in principle use as input to my agent, to my controller, the entire flow field. But if you think about a realistic application, let's say a real wind farm or a real truck with real sensors, the best I can do is I can place a few pressure sensors here and there, and that's all I can do, right? So I can only sense at a few limited locations. So in a formal sense, we can say that we are transitioning from an MDP, a Markov decision process, to a PO-MDP, a partially observable Markov decision process. So, for the rest of the talk, I really want to focus on this last point. So we really try to kind of find, first of all, a way to even study this problem in isolation. Of course, these more realistic applications and projects that I mentioned in the first two slides, they suffer from all of these issues. But so we first of all want to find a setting where we can study this, this particular problem of having only partial information about the flow state in isolation. What we decided on is a simple one-dimensional partial differential equation known as the Kuramoto-Sivashinsky equation, which is this PDE you can see right here. And the main things you should know about it is simply that it does model a variety of unstable phenomena, and it has this parameter nu as well here, which is a positive parameter such that as nu becomes smaller, the dynamics actually becomes increasingly chaotic. So on the right-hand side here, what you can see is a TX plot of a solution where, in this case, the forcing term F on the right-hand side is 0. So we're just solving the homogeneous equation. And we start at time 0. It looks like 0, but we actually have a tiny, tiny perturbation of 0. So we're not exactly 0. And because the 0 solution is very unstable, as we solve, the solution will converge to the chaotic attractor, which is sort of this, visually can be described as these noodles which sort of emerge and merge and move around like that. And okay, so what is the control problem? So we then add in this right-hand side forcing term, and essentially we just try to stabilize the 0 solution, right? So if we don't stabilize, we converge to the chaotic attractor, and we would like to kind of stabilize around 0. Now, let me describe the setup, the RL, the feedback loop or the control problem. So we have, of course, a numerical solver for this equation. And we start out by solving for a few time steps. So the solution changes and changes and changes. Now we're done solving. Now we're done solving. So what we will do is we will stop the solver and then we will partially sense the solution, right? So we will pick a few finitely many locations in the domain and simply evaluate the solution at these few locations. Let's call that number capital S is the number of these locations. Then this partially sensed solution is then fed into the controller, which then needs to update the forcing term. And once the forcing term is updated, that gets fed back into the solution, and hopefully we can stabilize around 0. Now, let's think about if this is a good problem. So the first thing we did, of course, is we looked at, we implemented a controller, right, which is a particular controller known as TQC, or truncated quantile critic. That's just a particular kind of state-of-the-art reinforcement learning agent. And we trained the agent for various different numbers of sensors. So we decreased the number of sensors. So we're only allowed to sense or to evaluate the solution at less and less points in the domain. And unsurprisingly, as we use less and less sensors, the performance decreases. I should explain this L here is simply the L term of the solution at the last time step. So this means since we're trying to stabilize around the 0 solution, L being close to 0 is good. L being far from 0 is worse, right? So what we can see, as the number of sensors decreases, indeed, so does the performance. So now we know that we have a good toy problem, a good problem that allows us to study this problem of partial observability in isolation. The next question is, what can we do about it, right? So how can we fix this? And the idea is, because I only have partial information about my system at each time, what I will do is I will keep track, I will incorporate some kind of memory and essentially keep track of things that I have seen in the past in order to be able to reconstruct, or to better be able to reconstruct the full state. So let's look at this diagram, this reinforcement learning feedback loop that we've seen before. And so now, instead of the state ST, the environment only gives us this partial observation. Let's call it OT for observation. So if I just expand the agent a little bit more and make some space, so basically a standard reinforcement learning agent would do this. You take essentially the observation, map it through a neural network, and output your action. Of course, it's not quite that simple. This is a simplification. Other things will happen inside that agent too that relate to, of course, aiding and sort of enhancing and speeding up that convergence. But more or less, at the end of the day, this will happen. Okay. So the idea is next, let's add in a memory term, which the agent is allowed to keep track of. So the agent has an internal memory now. And what we first do is we take our observation and the previous state of the memory, update that memory to make, to get an updated memory. And then we map this memory together with the observation into the neural network to again produce the action. So the main question here, of course, is, how do we incorporate memory? And how do we do that in the best way possible for the applications we have in mind? So basically, there's 3 different paradigms which you could come up with. One is a ring buffer, recurrent networks, and attention. So let me talk a little bit more about these. So the ring buffer is kind of the simplest thing you could possibly imagine. It is very simply you stack your a certain specified number of past observation. You stack that into a big matrix. And that's your memory, right? And as new observations come in, the oldest ones they fall out of the memory like this. This is also known as frame stacking in reinforcement learning. The other option is to use recurrent neural networks like LSTMs or GRUs. And finally, recently there has been more of a push to use attention-based methods such as transformers. So if you haven't heard of this, attention-based methods or transformers are models that originated in large language models and then also vision models, such as ChatGPT and so on and so forth. And they are essentially some kind of alternative sequence models. So let me sort of explain a little bit the structure, sort of the architectures we considered. So in our study, we then we compared 3 different agents. One is an agent that doesn't have any memory at all. One has an LSTM as a memory, and one has a new kind of memory that we christened chaos robust transformers, or CARROT. which uses transformers. So this diagram, let me not spend too much time on it. Instead, I want to give you a slightly simplified overview of what of how we use attention to update memory. So we start out by having our memory matrix. So essentially, the memory is a matrix consisting of these. So you can think of it as a stack of row vectors, right? So we have M1 to MK. So what we start by doing is we start by stacking up these row vectors, so the previous memory, and we append to it another row, which is the new observation OT. Then what we do is we basically just compute some a convex combination of all of these rows, where the weights will actually depend on the weights will actually also be function of the observation. Okay, so we compute a convex combination of all of these, we sum them up, and then we have the first new row. So we produce the first new row of the updated memory, M tilde 1. Then we repeat this process several times. So we compute a new set of weights sum them up, and produce the second row, a new set of weights, produce the third row, and so on and so forth until we're done all the way and we have produced a new memory matrix. And then basically we just, some more stuff happens. So we map this again through a neural network, layer normalization. We do a learnable, slow-moving linear update to basically regularize the training. But more or less, this is kind of what happens. So this is this concept of attention. We pay different amounts of attention to each memory to update it. Okay, so very quickly, let me just show you the results. Indeed, this attention-based architecture carrot performs better. So this is the convergence plots, and then again the final energy, the final L2 norm of the solution at the last time step. And you can see, again, let me point out, L being small is better, right? Because we want to be close to 0. And you can see, indeed, convergence is more robust, faster, and just overall a better performance. And in fact, this result still holds true if we go to very, very chaotic regimes. So if we vary this parameter nu, if you recall, controls how chaotic the regime is, the smaller it gets, the more chaotic it becomes. And if we make the system more and more chaotic, what you can see is a trend that the more chaotic systems in general have worse performance, but carrot or attention still manages to outperform. So in summary, I don't have a summary slide, but in summary, this is just one piece of this super complicated puzzle of making realistic turbulent flow control work. This is one small aspect of it, is the partial observability. There's many more aspects, and I'm hoping we can soon tell you more cool results. Yeah, so that's the end. These are some references in case you want to look up some more details. Thank you.
Thanks, Max. Really, really nice talk. Really enjoyed that. Right, I think, again, if anybody has questions, please do pop them into the comments bar. I don't see any there right now, so we'll just fire away from the chairs. I was really interested in the results. Can you, I think that second last slide, you showed the kind of convergences of the different methods. Why does the convergence of the no memory get such good early results and then start to fall apart? Maybe I didn't quite understand this plot very well, but can you give me some intuitions as to how this happens?
Yeah, absolutely. So I don't know if I can really help with intuitions very much, but so essentially what happens here is something that tends to happen quite a lot with reinforcement learning agents when the convergence is brittle. So so essentially this is called catastrophic unlearning, and it's essentially something that that can happen whenever the convergence is sort of too brittle. So essentially what you might observe is that somehow some agents will converge really, really well, and other agents will deconverge very horribly. Yeah, essentially why exactly it happens, I don't think I can answer that exactly, but it is something you can frequently observe in also, let's say, more classical reinforcement learning setups when maybe the hyperparameters might not be super well tuned or things like this. So I guess overall the point is sort of carrot, initially converges slower, or having an attention-based memory means you converge a little bit slower first, but you do converge very robustly in the end. Yeah,
thanks. Ahmed, do you have a question? I've got a
thank you, Max, for the very nice talk. First, there is people online as well. They are thanking you for the informative talk. Sasha just posted a note there. I really like the idea of let's fall back and understand the problem. But I wanted to be pushed back a step further. Your question now is, what is the structure of the policy network which can control the system? And if we want to move step back, Markov decision process, which with full observation, is a deterministic process. You have UT, you have action T, you know the next one. Partial, the process becomes non-deterministic. So here, the figure you are showing us is complicated because the neural network is embedded in another reinforcement learning algorithm, which have its own properties. Maybe it's PPO, maybe it's Dreamer. How about predictability of the system under random actions? Try to predict next state or next partial state, given the architecture of this neural network. If you are just trying to, will you have similar, because now we don't have the solver steps. It is just the size of the training data. I'm not sure if I'm explaining what I'm talking about, but I'm trying to, if we are to generate extensive data sets based on random actions, but this is, again, random action is not good actions where you are dampening the system as well. So random actions are, here your action goes from one regime at the start to something else at the end. So they are different properties.
Yeah, I mean, absolutely. I completely agree. It's almost like a bit of an artificial kind of setup, right? Where we're considering a baseline RL agent. So in this case, it was TQC, right? But you completely right. It could have been anything, or it could have been SAC, it could have been TD3, Dreamer, like you say, right? And then we're sort of saying like, okay, let me modify essentially the policy and the critic network and whatever to give this agent memory. But of course, there is many properties of the RL agent itself, which will interact with these networks in an, I think, arbitrarily complicated way that cannot be really detangled easily, right? It's not really easy to say, okay, can I now take this and can I plug it into Dreamer and will this be better or will it worse? Okay, it's really difficult to say. So definitely I agree. I mean, the main motivation, I think, for setting it up in this way was that I think, like I showed in the very first slide, we have this project with in the wind tunnel where we have this truck, where we're trying to optimize the flaps. And in some sense, I guess the idea was, how can we get better convergence for that, right? And so I guess it was a very kind of practical approach, as opposed to like, fundamentally, I'm not sure, what does this reveal about the optimization properties of such systems? I don't think very much, right? But it does show, okay, if you wanted to use TQC, that might help you get better or more robust convergence. But does that apply across all algorithms or across different optimization strategies? Probably not. Yeah.
Another question: why invent another transformer-like algorithm? The transformer algorithm, if you look to the historical part of it, was missing somehow normalization, square root size of the dimension. So, and it have evolved over generations. Some people claim it's just 7 years ago, or some people consider it is 27 years ago. Versions of it have been somehow proposed, but the version which is implemented in the state-of-the-art NLP algorithms have normalization parameters in it, depending on the size.
That we have that too. So
your version?
So we're using something called an identity reorder transformer. So Basically, people have tried to use transformers a lot in reinforcement learning. So essentially, I think until recently, the consensus was somehow that it is quite difficult to make transformers work in the same way that an LSTM might. So in particular, one thing people found is something called a gated transformer, which again uses this sort of identity reordering. And so there were some various experiments where they just made these small modifications to the transformer and then plugged it into an RL algorithm and kind of see, okay, how can we get better convergence? So what we did is we essentially took this identity reorder transformer. So this kind of very simplified description I gave obviously did not do this justice. So the actual implementation is the identity reorder transformer, which has all of these normalizations built in. But I just wanted to give like a very quick explanation of the concept of attention somehow. But definitely, I mean, it is basically a normal transformer. The only difference being that we're using it as a memory term, and the difference is that we're using, you could call it cross attention in the sense that the input sizes are slightly different, right? Because you have an input size of memory plus observation, but the output is sort of squashed down to memory. But it is effectively just a transformer with minor modifications. Yeah.
Thank you.
Yeah, thanks. We are running low on time, but I did want to ask one quick question kind of around the application and like how you validate and test that this would work, and what types of sensors. You mentioned the sensors, but obviously this is like in a virtual environment. I guess when you put this into a real environment, how will we tell the performance, and how could you implement this type of thing in a real-time kind of control environment?
Yeah. So in this particular example of the wind tunnel experiment, I mean, the way it's implemented is there's a force scale. The whole thing is mounted in the wind tunnel on a force scale, so you can immediately measure the drag force directly. You measure the X force, right, of the wind. And I guess maybe, if I understand correctly, you may be asking a little bit about how would you put this into a real wind farm? Yeah,
exactly. Especially like the sensor bit, because I'm a chemical engineer, so my background is very much not in this area, but I'm quite interested to know like what the mechanics of it would look like.
Yeah, definitely. So for this project that we're working on here on the wind farm optimization, basically. So apparently I'm not, I'm expert on wind farms, but I've been told that what's happening with very new wind farms is that they're installing LiDAR sensors on some of them. And these LiDAR sensors essentially allow you to sense the flow field a little bit past or before the wind turbine. So you get some limited information about the flow in the vicinity of the turbine in some kind of 3D. You get some 3D information actually, right? So this is what we're trying to replicate, but of course it's quite abstract, and certainly, I mean, there would be a huge step, of course, from taking something like this from a simulation to a real model. And again, I think reinforcement learning is very notoriously bad at this. So this transferability from one domain onto another domain, or from a simulation domain onto a real domain, is notoriously difficult. I mean, there is lots of, again, like innovation and lots of different algorithms for this, but it's notoriously hard to actually transfer RL policies from a simulator to a real world model, to real world engineering application. Yeah.
Great, thank you very much. I think that is our hour up. So thank you very much for really good talk, and also really nice discussion. Really enjoyed that, and we'll see you all next week, Tuesday. Right, Ahmed, do you have any information? Sorry about the next talk. You're on mute.
Apologies. Yeah, we are excited to announce our next session, which will take place next week, the same time, Tuesday, the 10th of September at 2 p.m. UK time. In that session, Professor Hongjian Sun from Durham University will present an overview of Durham University Smart Energy Research. Again, we initiated this AI for Net Zero webinar series by the 7 projects which have been funded through UKRI funding called an AI for Net Zero. So the first 2 months talks will be
by the PIs and co-PIs from these projects. But then after that, we will expand beyond that to the entire research community within the UK and Europe and probably US if there is shared time zones. Thanks again to the speakers, and thanks to the host of today, Professor Michael Short, and we look forward to seeing you next week. Bye now.